Hello and welcome to the second part of Lesson 2. In this video we're going to be continuing our mathematics survival guide and focusing on some of the essential elements of vector calculus that you'll need for this course. As ever, there's far more depth to the topic to be found elsewhere, especially in Faith Morrison's book that forms part of your recommended reading. However, what I've tried to do here is to give you key results and key relationships that you'll use frequently throughout this course. Hopefully, it'll also stimulate some intuition and embed some of the key learning points from the last part of this lesson. I'm going to focus primarily on how to use the gradient operator with scalar and vector fields, and give some examples of this operator in Cartesian coordinates. However, let's start by reminding ourselves what gradients actually are. So here on the board, I've got a schematic diagram of a hot steel bar. It's a one-dimensional bar. It's being heated at one end, the hot end, and it's being cooled at the other end, the cold end. And the only direction in which heat can flow is from the hot end to the cold end. I've put so much insulation on the other surfaces that no heat can escape. And so, if we were to draw a temperature profile of this bar, it would look a little bit like follows. Along the center line, we would start at the hot end, and we would exponentially decrease in temperature down to the cold end. And for those of you with a chemical engineering or mechanical engineering background, you might remember that the rate of heat transfer is proportional to the temperature gradient, and in this case the statement gradient is utterly unambiguous. We've got one parameter changing in one dimension, so we can simply take the tangent to this temperature profile and find the gradient at any point of temperature with respect to x. Life is good. Life is easy. However, life isn't always simple, since very often we might have a scalar parameter, like temperature, changing in more than one dimension. So here on the board I've put another schematic diagram of a more realistic heat transfer situation. I've still got my steel bar. However, what I'm doing this time is heating at the hot end and cooling at the cold end as before, but I haven't insulated the rest of it. So heat can escape from all the edges, and so heat can flow now in the y direction as well as the x direction. And the somewhat schematic colours on this diagram show perhaps maybe what kind of internal temperature profile might form. So now when we talk about gradient, we've kind of got a gradient both in the x direction and the y direction. So even though the measure of temperature is a scalar quantity, it can now change in two different directions. So the temperature gradient, strictly speaking, is now a vectorial quantity. And we can write the vector thus. It's, for two dimensions, a column vector with two entries, where we have the gradient of temperature with respect to the x direction in the first row, and the gradient of temperature with respect to the y direction in the second row. And note here I've used partial derivatives now, rather than total derivatives, because temperature is changing partially in x, but also partially in y. Hence, the convention is to use the partial derivative symbol. We can also, in shorthand, give this the notation grad t. The upside down triangle here is a gradient operator. It is vector in form, and what it consists of is simply a vector of differential operators. So in Cartesian coordinates in 3 dimensions, it's a column vector, and it's d by dx, d by dy, d by dz, stacked one above the other, where d in this case is partial derivative rather than total derivative, because we're changing the gradient of that parameter in more than one dimension. So we could write the gradient operator in summation notation, and in summation notation it appears thus: it's d by dxi ei. There we have our basis vector saying, look, we've got a different position that each of these d by dxi's needs to inhabit in the final answer, and we're simply going from I equals 1 to 3, so it's d by dx1 e1, d by dx2 e2, d by dx3 e3, where 1, 2 and 3 are my different coordinate directions, and so for Cartesian coordinates 1 is x, 2 is y, 3 is z. So we can take gradients of not only scalar quantities, but we can take gradients of vector quantities as well. So let's explore this a little bit more. We've just encountered the upside down triangle, grad or nabla or del. It goes by a number of different names. And we've just said that we can think of nabla as a vector of differentials. So let's see what happens when we consider this vector of differentials operating on a vector field. Let's say what we're interested in is the rate of change with respect to distance of velocity. I'm going to restrict my example to Cartesian coordinates because they're far more straightforward to evaluate. In your notes, I've also put some examples of how we can write all these derivatives in cylindrical polar coordinates and in spherical polar coordinates. But in Cartesian coordinates, we can write the gradient of the velocity field, grad v, as an outer product, grad outer product v, because we've got two vectors operating on each other, and so the answer is going to be second rank tensor. And grad v, or grad outer product v, is going to be a quantity that we will see quite a lot in the lessons that follow, because it gives us velocity gradient information. And velocity gradient information is essential to finding out things like rate of strain. More about that in lesson 3, however. Let's focus for now on this outer product, nabla or grad or del outer product v. Nabla here is our column vector, d by dx, d by dy, d by dz. V I've transposed, as we saw in the definition of the outer product last time, and that is now my row vector, vx, vy, vz. And so we expect the result to be second rank tensor, and we can see that is exactly the point. So I've coloured here the different components of both the row vector and the column vector, so you can see which has operated on which. So on the diagonal of the final result, so the 1, 1, 2, 2 and 3, 3 position, we've got dvx by dx, dvy by dy, dvz by dz, so pink, green and orange. If we look at the first row of the result, we got dvy by dx, dvz by dx. So that first element in the column vector is operating on each column of the row vector. And it is the column of the row vector that denotes which column the product goes in the final result. Likewise, it is the row in the column vector, d by dx, d by y, d by dz, that denotes which row that product goes in the final result. So if we look at the d by dy and the vz, d by dy is on the second row of that column, so expect it to be in the second row of that final matrix. Vz is in the final column of the row vector, so we expect the result to be on the second row final column, and there you can see dvz by dy. So not only is this a reminder that the outer product of two vectors is a second rank tensor, it also gives you an example how to operate on a vector with our gradient operator. So much as we had outer product and inner product when we're thinking about vectors, we've got the same with the gradient operator and vectors, because the gradient operator is just simply a vector of gradients. So let's look at the inner product, or the dot product. In respect to thinking about velocities and velocity fields, the inner product of my gradient operator with the velocity field has a very special term. It's called a divergence. And we'll see in lessons to come, this has a very distinct physical meaning. It's effectively a statement of conservation of volume, but we'll touch on that in lesson 4. For now, let's just focus how, in Cartesian coordinates, we can write this divergence down. So we've got an inner product, gradient operator, dot product v, or gradient operator, inner product v. We have the row vector to start with, d by dx, d by dy, d by dz, operating on the column vector, vx, vy, vz. And we know the result is scalar, and it is the sum of d by dx of vx plus d by dy of vy plus d by dz of vz. And so there we have the final result written out for you. And again, we're going to be touching on the physical meaning of this a lot in lesson 4. So we've done first derivatives. We've met the upside down triangle. Let's think about second derivatives. So we often come across a quantity where we get the square, or what looks like the square of the gradient operator. This is just like writing d2 by dx squared, or something of that nature. And so the second derivatives with the gradient operator is called the Laplacian. And the important thing to note here is that it is a scalar operator. So let me write its expansion for you in Cartesian coordinates. The Laplacian, del squared or nabla squared, is equal to d2 by dx squared plus d2 by dy squared plus d2 by dz squared. And so we can see from that sum, we do indeed have a scalar result. So the Laplacian of a scalar field, let's say Laplacian of temperature T, is simply d2t by dx squared plus d2t by dy squared plus d2t by dz squared. Again, using partial derivatives because temperature is changing both in x and in y and in z. We can also take the Laplacian of a vector field and we end up with a vectorial result because the Laplacian is simply a scalar. So we can think about the Laplacian of a vector field which has components vx, vy, vz, with vx, vy, vz each changing in the x, y and z directions. And so we end up with a column vector where the first row is d2vx by dx squared plus d2vx by dy squared plus d2vx by dz squared. And we see vx is what is being taken the second derivative of at every point with respect to x, with respect to y, with respect to z for that first row. And then the second row is with respect to vy, and the third row is with respect to vz. So, again, we have to be slightly careful when using the gradient operator on combinations of parameters. So let me just run through a few basic rules for you. Number one, grad t, or nabla t, is not the same as t nabla. And we can reason this as follows. Grad t is dt dx, dt dy, dt dz. The gradient is operating on t. The gradient operator is vector. We end up with a vectorial result. Inverting that reasoning, t now is just simply a scalar that's operating on the gradient operator. So t grad is just scalar t multiplied by the gradient operator. And it doesn't really make that much sense because the gradient operator now isn't actually operating on anything. So grad t is not the same as t grad. Let's think about the combination of the gradient operator working on two scalars multiplied together. Let's say we've got a random scalar field alpha and a random scalar field of temperature T. So grad of alpha T we can simply think of as a chain rule. If this was just d by dx of alpha T, it would be alpha dt dx plus t d alpha dx, which is exactly what we see with the gradient operator. Is t grad A alpha plus alpha grad t. So think of that scenario just like a normal chain rule. What happens now if we have the product of a scalar and a vector where the gradient operator is operating on? Again, it is a chain rule expansion. The only difference now is we've just got to be very specific what exactly is being operated on by the gradient operator. So we know that the gradient operator is a vector and that a scalar being operated on by a vector gives a vector, and vector cross outer product with vector gives us a tensor. So we know that, for example, grad A, or grad alpha, is now a vector. Outer product with velocity, which itself is a vector, gives second rank tensor. We can only add that second rank tensor to another second rank tensor. And so if we just simply have scalar alpha multiplying by grad V, we've already seen that grad V is a second rank tensor. So we're adding second rank tensor to second rank tensor, which we know we're allowed to do. So in both these operations in 2 and 3 on the blackboard, we've just simply invoked our chain rule, our product rule. And please don't forget, you can only add like to like. If we just think of one final example, let's say we've got two scalars added together in brackets. If this was just a simple d by dx, if we had d by dx of alpha plus t, it's just d alpha by dx plus dt by dx. Same with the gradient operator. Grad of alpha plus t is just grad alpha plus grad temperature, grad t. Now, you can only add like to like. We're going to be revisiting that statement a number of times throughout this course. I'm going to call it rank homogeneity, which is a bit of a mouthful, but it just says, look, you can only add like to like, second rank tensors to second rank tensors. We've got the rank is 2, it's homogeneous across the two, hence rank homogeneity. We can only add vectors to vectors, same thing, only add scalars to scalars. So please don't forget that. Let's make a brief note about different coordinate systems, because we've solely focused on Cartesian coordinates because they're relatively easy. We can, of course, write the gradient operator and the Laplacian in cylindrical polar, in spherical polar coordinates, and in any other curvilinear coordinate system. And it gets increasingly more complex. Now, in your notes, I've put tables that include the gradient operator, the Laplacian, the dot product with a vector, and the dot product with a tensor to show you what the expansions are. And hopefully these will be of use as you go throughout this course. But I'll just put some examples on the board for you now, just to illustrate the fact that they're different. So in cylindrical polar coordinates, the temperature gradient, remember it's a vector quantity, is written dt by dr, and then 1 over r dt by d theta, and then dt by dz. So if we think about the divergence of the gradient operator with a velocity field, for example, it's now 1 over r d by dr of rvr. It's not dvr by dr. So for goodness sake, don't fall into that trap. The next bit that gets added to it is 1 over r dv theta by d theta. Again, it's different. And then just simply dvz by dz. I'm not going to go into the reasons why it's different here, but again, if you look in Faith Morrison's book, there'll be a lot of information pertaining to that. My key take-home message I want you to get from this slide is that they're different. A final illustration of this is the Laplacian of a scalar temperature field in cylindrical polar coordinates. And now we can see the expansion is quite hairy. We've got 1 over r d by dr of r dt dr plus 1 over r squared d2v theta by d theta squared, and then d2vz by dz squared, which is very different from our Cartesian form, which was just d2t by dx squared plus d2t by dy squared plus d2t by dz squared. So please do remember that in cylindrical polar coordinates and in spherical polar coordinates, the expansions of the gradient operator and the Laplacian and of the dot product are all a little different to what you might find in Cartesians. So let's just sum up a few key points. What I want to try and communicate is that the upside down triangle is just differentiation in more than one dimension. We call this upside down triangle nabla, or the gradient operator. The gradient operator is a vector. The second derivative form, the Laplacian, is a scalar. So when we use the gradient operator and we use the Laplacian, we need to remember the rules of how to use scalars, vectors and tensors together. And the key take-home message here is don't forget you can only add like with like. That's the concept of rank homogeneity. The final thing to remember is that the exact form of the gradient operator, of the Laplacian and of the divergence depends on the coordinate system. I've used Cartesian coordinates here because they're easy to illustrate the points I want to illustrate. However, if you're solving problems in cylindrical polar coordinates or in spherical polar coordinates, do be careful and do look in your notes for the full expansion of those operators.